Welcome to the University of Vermont College of Engineering and Mathematical Sciences Engineering Week site. This site is designed to help you or your students do well at the Engineering Week competitions held each year at UVM. This is a two-part series, and this is the start of the second part. We have already discussed how to mathematically model your bridge or truss, and now we will talk about building it and then testing what you have created. Let's get started. Now back to pasta. We will now move from designing to fabrication. If you are building a pasta bridge, you will be making two identical side trusses and then joining them together. If you are making a wooden truss, you will need to build only one. Either way, you will need to start by making a full-size drawing on graph paper. Make sure that your drawing conforms to the design specs in the rules. When engineers work professionally, they are given a set of design specifications that they must work with and adhere to. If the solutions they propose and develop do not meet the design specs, the engineers don't get paid, and that's no fun for anyone. Once you have your drawing, start by testing gluing some pasta. Make sure you have enough glue, but not too much. Hot glue is heavy and does not add that much strength by itself. It tends to creep. After you've tested a few pieces, try breaking them in both tension and compression and twisting. Note that the top chord is thicker in this drawing and in the fabrication than the bottom chord. You can do some trimming if the glue sticks out or the pasta sticks out with a hacksaw or a sharp razor knife. I also use the tip of a glue gun sometimes to smooth out unnecessary glue. It's a good idea to place wax paper over your drawing. You can see where the pieces need to go, and the wax paper will protect your drawing. Here you can see the top chord of a wooden truss design. Screws are used to hold the curve to the design specs while the glue dries. It also helps to keep the wax paper, the drawing, and everything aligned during the fabrication process. My students create several iterations, different fabrication techniques, from the same set of drawings. They try different ways of fabrication and different gluing techniques. These students translated their design to a CAD/CAM system, computer-assisted drafting and computer-assisted manufacturing, and had a computer-controlled router do the cutting for them. This is the type of work that professional engineers often do. You may not have access to a computer-controlled router in or near your school, but if you do, go for it. It will develop the skills that you will need later in life. Here you can see that the router has cut where it was not supposed to. This is because the board slipped. It wasn't clamped properly. The programming was good, but the fabrication technique needed to be improved. Oops. Here is a finished truss member ready to be laminated with others to make into a final competition truss. Here a student is ready to add the last few members to her design. You can see that each member is laid out over the drawing, cut to size, and then fitted and glued in place. This is a drawing of a real type of engineering structure. Real truss structures reinforce their joints by adding gusset plates. It was a gusset plate that failed on a bridge in America a few years ago on the interstate, resulting in several deaths. Here is a typical gusset plate in a real-world application. This student has added gusset plates to each side of her truss. She designed the plates to be as small as possible, but still provide the structural support necessary. You notice that the truss is below the drawing, and you can see the drawing and the truss are similar, but not exactly the same. This design does not need gusset plates. This was not the final competition fabrication. Notice the sloppy craftsmanship. Too much glue adds unnecessary weight. My recommendation is to build several trial trusses and test them to see what works and where they fail. You should be able to make a truss in about 20 minutes using hot glue. For your final competition truss, use wood glue, and this will take more time to build and dry, but will give you better results in the competition. Students here are testing an iteration of their design. And iteration is when you try a design and then change it and test it again. It is much easier to test iterations in software than with wood or pasta, but the software is only an approximation of reality. Nothing beats a real-world test. Here you see the chain and the bolt is supported to a lever that has buckets of weight added to it. This is similar to the type of testing device that will be used in competition. This concludes this photo story. Our hope is that the photo story will help you get ready for the eWeek competitions held each spring at the University of Vermont, College of Engineering and Mathematical Science. This competition was designed to help you develop the skills that will prepare you to do the work of an engineer. All types of engineers develop models, test them using mathematical modeling and/or software, develop many iterations of their work, and then develop their final designs. We hope to see you at this year's eWeek events. Engineers are working on solutions to people's needs worldwide to help them solve their problems. This is Tom Taylor saying that engineering rocks my world. I hope it does for you too.